Okay, colligative properties. Have you ever made ice cream at home? Some people have. So if you have the traditional type of ice cream maker, you've got an inside container where you put the milk and the sugar and stuff, and then you have an outside container that you put ice in. But you can't just put ice, you have to put salt on the ice. Do you know why? Adding the salt makes the ice colder. Does that seem wrong? It seems wrong. But adding the salt lowers the temperature. A saltwater solution freezes at roughly minus 10 degrees Celsius instead of at 0. Pure water freezes at 0. When you have a solid and its liquid together, it's going to be at the freezing point. So as the ice begins to melt, without any salt in it, it's going to be at 0 degrees Celsius. You add salt to it, it's going to drop down perhaps as much as to minus 10 degrees. So this is a depression of the freezing point. The freezing point is going down, it's being depressed. This is what we call a colligative property. This is a set of properties that depend on the number of particles that are dissolved in the solution. They do not depend on which particles those are. So if you use sodium chloride or potassium chloride or some other salt, it wouldn't matter. You'd see the same freezing point depression. We do get different effects depending on whether we've got an electrolyte or a non-electrolyte. So salt is an electrolyte. It's an ionic compound. When it dissolves in water, it separates into 2 ions. It gives us 2 particles for 1 mole of salt. Something like sugar is a molecular compound. Sugar dissolves in water, but if you have 1 mole of sugar, you get 1 mole of particles. And so it's going to take more to get the same effect. It depends on the number of particles. Vapor pressure lowering is another colligative property. The vapor pressure of a solution containing a non-electrolyte is lower than the vapor pressure of the pure solvent. So let's look at how this could happen. Here we have a beaker with a watch glass, so a closed container. This is water. The water evaporates and begins to condense, and we get a dynamic equilibrium where we have water in the liquid state and water in the gas state, and this pressure is the vapor pressure of water, depends only on the temperature of the water. We learned that earlier. If we put sugar into the water, now there are some sugar molecules in here, and some of those sugar molecules may be at the surface, and they are going to get in the way of water molecules leaving. And so water molecules have a harder time leaving. So I had the Red Rover analogy. So now you're playing Red Rover, but there's some people just standing in the way. They're not playing the game, they're just standing in the middle of the field, making it hard for you to get across. So fewer people are going to make it through the line. So it blocks some of the surface. So the rate of evaporation will decrease. The rate of condensation will continue until it establishes a new equilibrium, but now there are less gas particles than before. The vapor pressure is lower. That makes sense? So that's, kind of a anthropomorphic way of looking at that, but let's look at a more fundamental explanation based on entropy. Nature likes to mix things. This is pretty trippy. So let's say you put 2 beakers under a glass cake cover. So here you've got a beaker with pure water, and here you have a beaker with sugar water. And you leave this for a long time. You come back, and the water level in the beaker that has the solute in it, the sugar in it, is higher than the level of the water in the beaker that just had pure water. That's like some weird magic trick, right? How do you get liquid water from this beaker to that beaker? There's no tubes or anything. Nobody came and siphoned it out or moved it. It's going through the air. It's going through the gas state. So we have evaporation occurring in both of these. The rate of evaporation here is going to be greater because you don't have any solute molecules in the way. And then we have, so we're going to end up with a vapor pressure of water under this covered plate. And then you're going to have condensation into both of these. Because the rate of evaporation is less here, but the rate of condensation is the same, the water is gradually moving from this side to that side. And this corresponds with that tendency of mixing, of trying to reduce or make everything the same, lowering this concentration and to get it the same as that. Of course, that can't happen, but it'll go in that direction. It makes sense that if we had the pure solvent and a concentrated solution in the same beaker, they would mix together to form a less concentrated solution. It's just not as apparent that that will also happen in a closed system with two separate containers. Kind of freaky. Well, we can quantify vapor pressure lowering. It's Raoult's law. So the partial pressure of the solution equals the mole fraction of solvent times the vapor pressure of the pure solvent. So if the mole fraction of solvent is 1, that would mean that it's pure solvent, right? If this mole fraction is 1, 1 times the vapor pressure of the pure solvent would still be the vapor pressure of the pure solvent. As the mole fraction of solvent decreases, that means you're getting more and more solute, then the vapor pressure will decrease. So when we look at vapor pressure lowering, delta P, the change in the vapor pressure is equal to the mole fraction of the solute times the vapor pressure of the pure solvent. So these two different formulas can be a bit confusing because one of them is mole fraction of solvent, one is mole fraction of solute. But think about extremes. If this mole fraction of solvent is 1, that means it's pure solvent, and 1 times this will give you the pure solvent vapor pressure. If the mole fraction of solvent is 0, there's actually no solvent there, what would you expect its vapor pressure to be? 0. Down here, delta P is the change in the vapor pressure. If there was no solute, would the vapor pressure change? No. If there's no solute, then the mole fraction of solute is 0, and delta P would be 0. So thinking about it that way can help you keep track of which one's solvent, which one's solute. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. The temperature being specified here is because we need the vapor pressure of pure water. And so if we had to go look it up, we'd need to know what temperature. So we want to calculate the vapor pressure. We don't want to calculate the change in vapor pressure. We just want to calculate the vapor pressure. So we're going to use Raoult's law. The pressure of the solution is going to equal the mole fraction of solvent times the vapor pressure of the pure solvent. What's the solvent here? Ethylene glycol is a liquid, by the way, at room temperature. How do you decide which one's the solvent? It's the one that you have more of. The solvent is the one that's larger, and the solute is the one that's smaller. So then what we're looking at here is the mole fraction of H2O times the vapor pressure of pure water. Well, this is the vapor pressure of pure water. Vapor pressure of the solution is what we're looking for. We know this, so we need the mole fraction of water. So the mole fraction of water is going to equal the moles of H2O divided by the moles of H2O plus the moles of ethylene glycol. I'm going to call it EG for short. I know, it means something else, but that's why I capitalized it, to make it different. So we have to do some mole calculations here. We've got masses. So 55.3 grams of ethylene glycol. You need to convert that to moles. So grams on the bottom, moles on the top. This is written, there's the freight train, 20 minutes. This is written in a kind of a strange form. And it's to indicate the structure. We don't care about the structure. The train doesn't either. So we can just count up all the hydrogens. Just count carefully. I'm at 2, 4, 6. So 6 times 1.008. And there's 2 carbons, so plus 2 times 12.01. And there's 2 oxygens, so 2 times 16. So I'm getting a mass of 62.068. So we can calculate the moles. So 0.899095. So that's the moles of ethylene glycol, Eg. And we need moles of water, 285.2 grams of water, 1 mole for 18.016 grams. .830 moles of H2O. So for the mole fraction, we're going to have 15.830 moles divided by 15.830 plus 0.89095 moles. I'm getting 0.94671 as the mole fraction. So by moles, this is 94.67% water. So it'd be 5.4 something 5-ish percent ethylene glycol. The reason we have to go to mole fraction here is because vapor pressure change is a colligative property. It depends on numbers of particles, not on their mass or what they are. So because this is 94% water, the vapor pressure is 94% of the pure vapor pressure. But we're using this as a fraction, and so we've got 0.94671 as our mole fraction times the vapor pressure, 23.8, not 28.3, of the pure water. And so I'm getting 22.5 torr. Any questions? I'll take that as a no. So there we were talking about non-volatile solutes. If the solute is volatile, though, if it evaporates easily, then it's going to contribute to the vapor pressure of the solution, because it'll also be evaporating. In an ideal solution, it will follow Raoult's law at all concentrations for both the solvent and the solute. And in that case, the total pressure above an ideal solution is the sum of the partial pressures. So if you have a mixture of A and B, they're each going to have their own vapor pressure, and the total pressure is going to be the sum of the partial pressures. Of course, how many ideal solutions do you think there are? Probably none that are truly ideal. Some of them are closer than others. But non-ideal solutions don't follow Raoult's law because the solute and the solvent are interacting with each other. If the solute and the solvent like each other a lot, if they speak the same intermolecular force language, that's going to reduce how much they evaporate. If they dislike each other, that's going to increase the amount. And so we see some interesting deviations here. This is what we expect for an ideal solution. Here we have a vapor pressure increasing here, and here we have mole fraction of A. So where the mole fraction of A is 0, its vapor pressure is 0. Here, the mole fraction of B, the other component, must be 1, and so it is at its maximum vapor pressure. The total pressure will be A and B combined. So right here it matches up. As we increase the component of A until we get a mole fraction of 1, its vapor pressure increases also. And the vapor pressure of B decreases. So here, the reason that this is not 0 is because pure A has, I was looking at the wrong line. This is the partial pressure of B, so that does go down to 0, and I don't know, my words are gone. So this is the vapor pressure of pure A. So when it's pure A, the mole fraction of A is 1. And this line, the purple, is just the sum at each point of the red and the blue. Does that make sense? I explained that very badly. If you have strong interactions between the solute and the solvent, what that does is it causes the vapor pressure of each component to be lower than you would expect. because they're reluctant to leave. They don't evaporate as easily. It lowers their pressure. And so then when you add those together, you get a dip in this vapor pressure as well, the total pressure. If there are weak solute-solvent interactions, that actually encourages evaporation and causes each of the partial pressures to be higher than you would expect, and so you get this upward bow of the vapor pressure of the solution. So that can happen. This is another one that's kind of long and hairy. Calculate the vapor pressure of a two-component solution. So we got benzene and we got toluene. I'm going to call benzene B and toluene T. It's 25% benzene by mass. At 25 degrees Celsius, the vapor pressure of pure benzene and pure toluene are 94.2 torr and 28.4 torr, respectively. Assuming ideal behavior, calculate the following: the vapor pressure of each of the solution components. Well, let's label what we've got here. I'm going to use some space up here. So we have 25% benzene by mass. So that would be 25.0% B, which would equal 25.0 grams of B per 100 grams of solution. And we have some pressures. We have the vapor pressure of pure benzene is 94.2 torr. The vapor pressure of pure toluene is 28.4 torr. They want us to calculate the vapor pressure of each of the solution components. So this is going to depend on the mole fraction. Yeah. Blanking all of a sudden. So we need the mole fraction. The pressure will be the mole fraction of that component times its pure vapor pressure. So the vapor pressure of benzene will equal the mole fraction of benzene times the vapor pressure of pure benzene. Because when we add toluene in here, we're decreasing the mole fraction from 1 to less than 1, and we're going to be decreasing the pressure. So we need the mole fraction. Well, we've got 25 grams per 100 grams of solution. So that's the percent of benzene. What's the percent of toluene? 75, because they have to add up to 100%. So we've got 75% toluene, or 75.0 grams of toluene per 100 grams of solution. So here we've got this grams of solution, and we just want to get moles. The mole fraction doesn't depend on the amount of substance or mixture that we have. The mole fraction is going to be the same regardless. So what I'm going to do is I'm going to say, let's just say we have 100 grams of this mixture. Then I know the mass of benzene and the mass of toluene. So if I have 100 grams of solution, then I have 25 grams of benzene and 75 grams of toluene, and from those masses I could calculate moles and mole fraction, right? So to get the mole fraction of benzene, I need moles of benzene divided by moles of benzene plus moles of toluene. I've got 25 grams of benzene, and I'm going to divide by grams and multiply by moles, and I need the molar mass, 6 times 12.01 plus 6 times 1.008, 78.108. $25 divided by 78.108, 0.32006 moles of benzene. So I can plug that in up here, 0.32006 moles of benzene, and 0.32006 moles of benzene. Oops. And then I need moles of toluene, so that would be the 75 grams of toluene. And so I need the molar mass of toluene. 7 times 12.01 plus 8 times 1.008, 92.134. That's not equals, that's times. So 75 divided by 92.134. 0.81403 moles of toluene. So I've got 0.32006 divided by, open parentheses, 0.32006 plus 0.81403, close parentheses, equals, I've got a mole fraction of 0.28221 for the benzene. So then the pressure of the benzene will equal the mole fraction of the benzene, 0.28221, times the pressure of benzene when it's pure. So 26.584 torr. Any questions? We still need to calculate the vapor pressure of toluene. Let's do that in red. So the vapor pressure of toluene, P for toluene equals the mole fraction for toluene times the partial pressure of pure toluene, right? The vapor pressure. Do we have to do all of this over again? No, we don't, actually. There are two components here. Their mole fractions have to add up to 1. So we can find this mole fraction by taking 1 and subtracting the other mole fraction. So X, or is actually chi toluene, the mole fraction of toluene equals 1 minus the mole fraction of benzene. So 1 minus 0.28221. 0.71779. So we've got 0.71779 times the partial pressure of pure toluene, 28.4 torr. So that equals 20.385 torr. So 20.4 for the toluene, and 26.6 for the benzene. Any questions? See what's scary about this problem? You see that A? That means there's a part B. The total pressure above the solution. How would we find the total pressure above the solution? Just add the pressure of each of the components. So let's go back and get those numbers. 26.6 and 20.4. 26.6 and 20.4. 26.6. Ah! 26.6 torr plus, is it 20.4? Okay. The total pressure equals the partial pressure of the benzene plus the partial pressure of the toluene. 26.6 plus 20.4. So 47.0 torr. That's the total pressure above the solution. And then it asks us to calculate the composition of the vapor in mass percent. So we had, the pressure of benzene was 26.6 torr, and the pressure of toluene was 20.4 torr. So we were given the mass percent of the solution. This is asking what's the mass percent of the vapor above the solution. That's going to be related to the partial pressures. Okay, so this one can be a little bit puzzling. So the pressure of a gas is proportional to the number of moles of gas, right? And back in chapter 5, we had a little equation that we probably have forgotten. I'll do it with benzene first. The partial pressure of benzene is going to equal the mole fraction of benzene times the total pressure. So we know the partial pressure of benzene in this mixture. We know the total pressure. So from this, we can find the mole fraction. From the mole fraction, we can calculate mass percent. So rearranging this, the mole fraction of B is going to equal the partial pressure of B divided by the total pressure, which is the pressure of B plus the pressure of toluene. So the pressure of B was 26.6. I should be using the full numbers, but I'll use the rounded numbers. It'll be okay. So 26.6 divided by 26.6 plus 20.4. So this mole fraction is 0.56595. That's the mole fraction of benzene. The mole fraction of toluene is 1 minus that. So 0.434. 0.4. So mole fraction going to mass percent. So we need grams over grams of toluene or grams of benzene over the total number of grams. We've got mole fraction, moles of toluene over moles of benzene plus toluene. Anybody see what we need to do here? What do we need to do? So the convert mole fraction to moles and then to grams. We could say we have 1 mole of this vapor, right? If we had 1 mole of vapor, then these mole fractions would be equal to the number of moles of each of those. So we're going to assume 1 mole. So we've got 0.56595 moles of benzene. We need to convert that to grams. Anybody have the molar mass written down from the earlier slide? Hey Siri, what's the molar mass of benzene?
The molar mass of benzene is 78.1118 grams per mole.
Thank you. So 78.11 grams. So we've got 0.56595 times 78.11 grams per mole. So 44.206 grams of benzene. Then we take the mole fraction of toluene, and if we had 1 mole of the mixture, that would mean we'd have 0.43404 moles of toluene. Hey Siri, what's the molar mass of toluene?
Here's what I found on the web for what's the molar mass of toluene. Have a
Apparently people don't ask that as much. Like whoever asks that, right? 92.14. Yeah. 92.14 grams per mole. So 0.43404 times 92.14, 39.99. Grams of toluene. So then, to get a mass percent, I'm going to switch colors here. So the mass percent of benzene is going to equal the mass of benzene, 44.206 grams, divided by the mass of both of them, 44.206 grams plus 39.992 grams times 100. So 44.206 divided by the quantity, 44.206 plus 39.992, close parentheses, times 100, 52.5%. We have two components. The percentages have to add up to 100%. So we take 100 minus 52.5, we get 47.5, and so that's the mass percent of toluene. Yeesh, right? The liquid, the solution, is 25% benzene. The vapor is 52% benzene. So why is the mass percent of benzene in the vapor a little over twice as much as it was in the solution? Why isn't it the same? Which is more volatile, benzene or toluene? The benzene. The benzene has a higher vapor pressure, meaning it evaporates more easily. So the mass percent composition of the vapor is different than the mass percent composition of the solution, the liquid, because the vapor pressures are different. Any questions? So we talked about adding salt to ice and lowering the temperature of the ice. Oh, I'm jumping ahead. I was looking at this. Vapor pressure lowering occurs at all temperatures. This is a phase diagram. And so what we see here is that for a solution, the vapor pressure is going to be lower at all temperatures than the pure liquid. We also are looking here at melting points and boiling points, because the boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure, right? So if we're lowering the vapor pressure, that means that you have to get to a higher temperature before you reach a vapor pressure of 1 atmosphere. And you're going to get to a lower temperature to get the melting point. So what happens is we have freezing point depression, boiling point elevation. I used to have a hard time remembering which one went up and which one went down. They move away from each other. So it means that the substance will stay a liquid over a wider range of temperatures. So a solution has a lower melting point and a higher boiling point than the pure solvent. So to calculate the freezing point depression, that is the change in the freezing point. It's generally reported as a positive number. We know the freezing point is going down, but it's generally reported as a positive number. I'm sorry about that. The change in the freezing point is equal to the molality times a constant. So the molality, moles of solute per kilogram solvent. KF, freezing point depression constant, you would look that up in a table. Like this. So this is freezing point depression constant and boiling point elevation constants for several different liquid solvents. It also gives their freezing point and boiling point, the normal. So that would be at 1 atmosphere and a pure substance. Calculate the freezing point of a 2.6 molal aqueous sucrose solution. So this is aqueous. That tells us that the solvent is water. So we're going to need a constant. So the freezing point constant is going to be the one for water. 1.86 degrees Celsius per molal, and the normal freezing point is 0. So KF, 1.86 degrees Celsius per molal. The change in the freezing point is going to equal the molality times that constant. So 2.6 molal times 1.86 degrees Celsius per molal. .836 degrees Celsius. Is that the freezing point? No, that's the change in freezing point. To find the freezing point, which is what the question's asking, we have to start with the original freezing point, the normal freezing point, and subtract the change. So the normal freezing point of water is 0.00 degrees Celsius. We're going to subtract the change because we know that this causes the freezing point to go down. And that really doesn't require a calculator, does it? So it's minus 4.836 degrees Celsius. Rounding that would give us minus 4.8 degrees Celsius. The identity of the solute really doesn't matter. We need to know whether it's an electrolyte or not, because that would affect it a little bit, but whether it's sucrose or glucose or fructose doesn't matter. Any questions? Having some issues here. Okay, we did that one. Boiling point elevation. So the boiling point goes up. Same equation. The change in the boiling temperature is the molality times a constant. And the constants are in that same table. It listed boiling point elevation constants as well. So here we have a picture of someone putting antifreeze in the radiator of their car. Antifreeze is typically ethylene glycol. You mix it with water in your radiator. That causes the boiling point to go up, and it causes the freezing point to go down. So that extends the range over which the liquid in your radiator remains a liquid. This is a good thing, because where I grew up in Minnesota and Iowa, if you don't have any antifreeze in your radiator, there are some nights in the winter where your radiator would freeze solid. And water expands when it freezes, and so it would break, and that'd be bad news. But you also don't want your radiator fluid boiling, because that's when you get that situation where you're on the side of the road with all this steam coming out from under your hood. Not cool, literally. So by putting the antifreeze in there, that helps to elevate the boiling point so it can get hotter without boiling. So there's an application of colligative properties in everyday life. Let's calculate the boiling point of a 3.6 molal aqueous sucrose solution. Again, aqueous tells us that it's water. So we need to go back to the table. We're looking at a boiling point, so we need the boiling point elevation constant, and we need to know what the actual normal boiling point is. If you were doing this for chloroform or ethanol, then this is where you would find the boiling points. You would need those. So 0.512. So the boiling point constant, Kb, is 0.512 degrees Celsius per molal. So the change in the boiling point equals the molality times the constant. Molality is 3.60 times 0.512 degrees Celsius per molal. You see the units cancel out. 3.6 times 0.512 equals 1.8432 degrees Celsius. Is that the boiling point? No. That's the change in the boiling point. So the boiling point is going to be the normal boiling point, 100 degrees Celsius, plus the change. So 101.8 degrees Celsius makes the boiling point go up. Any questions? Another colligative property is osmotic pressure. So osmosis is the flow of solvent from a solution with a lower solute concentration to a solution with a higher solute concentration. This is the name of that process that causes dehydration when you drink seawater. You drink seawater, which is very salty, and that draws water out of your cells because they're going from a low concentration to a high concentration. I remember this as, well, nature's trying to dilute that to bring it down, trying to make everything equal. A semi-permeable membrane, semi means partial or part, so it's permeable somewhat. So it's permeable to some things, but not other things. It will, in this context, it will allow water to go through, but not larger molecules. All the cells in your body have semi-permeable membranes. Sometimes there's membranes within membranes, right? And it allows selected things to pass and controls how things move around in your body. So this is an osmosis cell. We used to call these U-tubes. We've got a semi-permeable, say that 5 times fast, semi-permeable membrane here, separating one half of the tube from the other. Over on this side we have pure water, and on this side, come on, pointer, come on, there you go. Over on that side we have solute particles, so let's maybe salt in there. So what's going to happen is that water's going to flow from the pure side into the salty side, causing the level of liquid on this side to go up and the level on this side to go down. We can think of this in terms of entropy, of spreading of energy. We can also think of this in terms of equilibrium. Here you've got water molecules. The water molecules are actually going both directions through that membrane, but they're going to go predominantly towards the salty side, the higher concentration. Because going back, you could think of it as the salt particles blocking the reverse movement. So we have a higher water level on one side than on the other. Do you remember the gas laws when we had these manometers and we were curved tube with mercury in it, right? And you can measure the difference in pressure by looking at the difference in the heights of the liquids in each arm. Well, this amounts to a pressure, and we call that the osmotic pressure. So you can measure it here. You could use like millimeters of water. It wouldn't be millimeters of mercury, it'd be millimeters of water. So the osmotic pressure has to do with how much higher this water level rises, or we can think of it as the amount of pressure you would have to apply to this side to prevent osmosis from happening. You've heard of reverse osmosis? They use that process for water purifying. Reverse osmosis, you're taking the dirty water, you're pushing it through a membrane and getting clean water. That doesn't happen spontaneously. It'd be great if it did, but it doesn't. You have to put pressure on this side. That's why it's called reverse osmosis. So it's doing the opposite of what osmosis does. Osmosis Jones. I used to try the osmosis method of studying occasionally, where you've got your chemistry book open and you're just so tired. So you put your head down on it and just sleeping, hoping that, you know, osmosis will go from the more concentrated knowledge into my head, which is less concentrated. It doesn't work. All that happens is that you drool on your book. Yeah? So we can predict the osmotic pressure. It's the pressure required to stop the osmotic flow. It's given the symbol capital pi. So pi equals molarity times the ideal gas constant times the temperature. That gives us the osmotic pressure. So M is molarity, of course, in moles per liter. Temperature has to be in kelvins. And ideal gas constant, we're going to use this one, the 0.08206, because then the units work out. So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. Osmotic pressure equals the molarity times R times the temperature, MRT. Well, they don't give us the molarity, so we have to calculate that. Molarity is going to be the moles of solute per liter of solution. So we've got volume of solution in milliliters. We can convert that to liters. And we're going to have to take this mass, 1.50 grams of ethylene glycol, and convert that to moles. So we've got 2 times 12.01 plus 6 times 1.008 plus 2 times 16, 62.068. So 1.5 grams divided by 62.068, 0.024167 moles. So then we put that in here, 0.024167 moles per liter. So divide by 0.05. So this gives me a molarity of 0.48334. So 0.48334. I'm going to use moles per liter so I can see the units work out. Ideal gas constant, 0.08206. Liter atmospheres per mole Kelvin. And temperature has to be in Kelvin. There's this Kelvin down here to help us remember that. And so 25 degrees Celsius is 298 Kelvin. So I've got my molarity times 0.08206 times 298 equals 11.8 atmospheres. It's a significant amount of pressure. That's the amount of pressure needed to prevent osmosis. Any questions?